it's going to go this way. B inside flows from south to north. See that? That's the key we were missing for that quick check problem, which we're going to return to. So I wanted to start off by that. Outside the magnet, they flow from north to south. But inside the magnet, in order to make a complete loop, well, that means inside the magnet, it must flow from south to north, the opposite. Right? And it only does that because this needs to be a circle, a complete circle pointing, with everything pointing in the same way. Does that make sense? So, right, everything's pointing this way. We know that B on the outside goes from north to south, north to south. Inside, it's going to complete that loop going from south to north. Okay? This is true for magnets that create magnetic fields, but what we also learned is that current-carrying wires create magnetic fields. And so we spent some time looking at all the different geometries, right? You can have a straight line of current. You can have a loop of current. Okay? So that's true also for those. So let's talk about that. So we know magnets create magnetic fields, obviously. Okay. So here, if we want to draw that picture, right, with the vectors to complete the loop, right, this line, this vector here, boop, boop, going that way, must connect over to this one. And you can see that inside it flows from south to north, the opposite. Right, inside flows from south to north. So just another picture showing you the same idea. Inside flows from south to north. So let's review this concept real quick. You know, Earth behaves like a magnet. Earth produces a magnetic field. And it gets a little confusing because the south pole of Earth, if Earth was a magnet, the south pole of Earth, magnetic south, is located at geographic north. Okay, so it's really, you know, it'd be really fun for me to put a concept problem on the exam. Okay, that tested that concept. Okay, geographic north is different than magnetic north. Right, geographic north not equal to magnetic north. They're in opposite locations. Okay, magnetic north is located at the south pole. Magnetic south is located at the north pole. And that's just one of those things where it's like we define north and south at a different time than we knew magnetic fields. You know what I mean? It's just like we didn't know at the time what we were defining, and then when the scientists came along and discovered magnetic fields and came up with the convention, it turns out it was opposite to the way we define geographic north. So then we got to the point where, guess what? Currents create magnetic fields as well, and that's what I have some fun demonstrations to show you, right? Moving charges also create magnetic fields, not just a bar magnet or a piece of iron, okay? So currents also create magnetic fields. We looked at a few different geometries. We looked at the straight wire, which produces a circular magnetic field. We looked at a loop, right? You take that straight wire, you form it into a loop. Loops of current create straight magnetic fields in the center. So you can think of it like flip-flopping, right? If the current's straight, then the magnetic field's circular. If the current's circular, then the magnetic field's straight. It's a cute way to think about it, okay? And then multiple loops of current will create a super straight uniform magnetic field in the middle. Okay? And then the direction of the magnetic field of all of those is given by the right-hand rule, so we're going to do lots of right-hand rules today. And the way that you use this right-hand rule is you put your thumb in the current direction, and then your fingers will curl around in the magnetic field's direction. And this works for straight wires, and it also works for curved wires. You just have to kind of move your thumb in a circular direction, right? So here for straight wires, pretty easy to do. Right-hand rule for curved wires, you'll need to take your thumb and move it around in the circle. So we'll do that. We're doing straight wires right now. Okay, straight wires create curved magnetic fields. Curved wires create straight, here we go. Right, so to see the magnetic field direction, you would take your thumb and you would, look at the top of the loop. We cut that loop in half, that purple dot in the green box, that's the current coming out of the page. So like your thumb is gonna be the current, it's gonna come out of the page, and then your fingers are gonna curl around it, and you can see that your fingers are making counterclockwise loops, which in the center of the current loop will be straight to the right, okay? And then if you look at the bottom, we take our current coming out of the top of the page, you go to the bottom, and your fingers are gonna curl clockwise. And what's neat is that you can see that in the center of the current loop, you have two vectors pointing the same direction, which means they're gonna add up to be pointing to the right in the middle. Okay? So you still use your thumb, but remember your thumb is always the current. You might be tempted here to put your fingers in I because you see a circular thing. But remember, your thumb is the current always. So if I goes in a circle, your thumb will need to trace a circle as well. Okay? So here's a picture of that for those of you that are going to be watching this video and you can't see me waving my hand around. Okay, your thumb will always be in the current direction. So let's get to, so is this the one that no, this is the one that we were fine with. Where's the one that we had? There we go. This one, the star. Let's look back at this. Now that we know about the inside, what magnetic field directions, how they point on the inside. So let me erase this. I'm gonna have to hold this because I don't have any pockets or anything to clip this. Okay, let's erase this. So the question is, what is the north magnetic pole of this current loop? So we'll use our right-hand rule, thumb in the direction of the current, to kind of figure out the magnetic field direction, okay? So I'm gonna start with my thumb coming out of the page on the right-hand side, and I'm gonna have counterclockwise magnetic field over here, right? And then I'll put my thumb into the page on the left-hand side of that loop, and I'm gonna have a clockwise magnetic field. And so the question was, what is the north and the south pole of this loop? So we know on the outside of the loop, our magnetic field vectors point from north to south, right? So on the outside, so what I'll do is I'll draw this on the outside. They point from north to south on the outside. So that means that this guy right here must be pointing towards south, right? And this guy right here must be pointing away from north. On the inside, it points from south to north, right? Which is, we're basically stating the same thing. The outside vectors point from north to south, but the inside vector technically points from south to north. It's all consistent, right? Just so the south pole would be on the top and the north pole would be on the bottom. And I'm talking about like outside of the loop area and inside the loop area. Outside points from north to south. That's this and this. Okay, let me use a different color. That's outside, okay. Inside points from south to north. Okay, so now it makes sense why the south pole is on the top and the north pole is on the bottom. Let's go back to what I did. Remember what I did? I drew this picture afterwards when I was looking back and trying to figure out what was going on here. what I did is, remember, I just drew one big vector like this, right? If you draw one big vector like this, then you might think that this is south and this is north, right? But you need to draw a vector for the outside and a vector for the inside. Then you can truly see which is the north and the south pole. Okay? So now we got that cleared up. Because that's going to come up a lot. We're going to do a lot of problems with that aspect. Okay, you need to know that. Any questions so far? Does that make sense? Kind of like what yeah, so we did some problems. We looked at the magnetic field created by the straight wire, the single loop, and then the multi-loop, which is what we call the solenoid. Okay, so we looked at all the field lines, and we do all of our right-hand rules, okay? And then we got to the calculation section. So we're gonna pick up in the calculation section. So we used the right-hand rule to find the direction of the magnetic field. Now it's time to find what is the magnitude of those magnetic fields. So we have different equations depending on the symmetry. For a straight wire, the magnetic field that's created by the straight wire is mu naught I over 2 pi r, where I is the current flowing. R is the distance from the current. And we use R because, you know, that the distance you are from the current is like a radial distance, right? So that's why we use R. It's kind of like a radius. And mu naught is our new constant, 4 pi times 10 to the minus 7, which comes out to be 1.26 times 10 to the minus 6. And then we did this quick check. And so we obviously, just like electric fields, magnetic fields are vectors, and the way you add them together like you do with any old vector, right? If you have a point in space you want to know the magnetic field of, like this blue point right here, well, if there's two sources of magnetic fields, then you'll need to add those two vector sources together. So here we have two sources. We have a magnet creating a magnetic field, which you kind of trace a little line, and then you draw your tangent right there. So there's one vector that we're adding, this guy right here. And then you have a wire creating a magnetic field, and so you're going to do your right-hand rule. You're going to see that it makes counterclockwise loops, and so then right at this point you would take the tangent. And so then these are the two vectors that you're adding together. Okay, so we're going to do some vector addition problems too, which is right here. This is what we're going to do. So we have two current carrying wires, and they're straight wires. And point P is above both of them. So the question is, what is the total magnetic field at point P? We have two long straight wires. They both have a current of 5 amps, but the currents are pointing in different directions. So our right-hand rule, we're going to have different vector directions, right? So let's do this. Let me copy it to another page. So the magnitude of our B fields is given by the general equation mu naught I over 2 pi r, right? That's our equation for the magnitude of a magnetic field created by a straight wire. And so each of these wires is going to create a magnetic field at location P. So if we're going to have two vectors, we're going to need to add them together. So what I like to do first is find the vector directions. Let's find vector B directions, okay? We're going to have B due to wire 1, and we're going to have B due to wire 2. So let's do the right-hand rule on wire 1. So our thumb is going to point to the left. And we're going to stop our fingers when they're above the current. So if the current is my thumb, it's coming straight at you. I'm going to stop my fingers when they're above the current. And that's going to be into the page direction. See that? Out of the page would be below the wire, but since I'm above wire 1, my fingers are curling into the page. So the B field created by wire 1 is going to be into the page, which is like represented by a little X. So into the page is typically negative. So like if we have our positive X pointing to the right, our positive Y pointing up, our positive Z would be out of the page, so into the page is negative Z. Okay, so a negative direction. Whatever, if you want to call it X, Y, or Z, it doesn't matter, but it's negative. So now, so this is into the page, which we'll call negative. So what about B2? The magnetic field created by wire 2. So our thumb will point to the right, because wire 2's current is pointing to the right. And then P is above the wire, so I'm going to stop my fingers when they're above my thumb, and that's going to be a B field pointing out of the page. So B2, I'm just going to draw it right here, but technically they're on top of each other, right? B1 is pointing into the page, B2 is out of the page, so we'll make this positive. So now we know how to add these things together, these two magnetic fields. So the total B field will be negative B1 plus B2, right? Negative magnitude B1 plus B2. So let's find the magnitudes. Mu naught I1 over 2 pi R1. I1, I believe it was 5 amps, right? And then R1 is going to be the distance that wire 1 is from the point, which is 8 centimeters, right? It's this distance right here. 0.08. Pi, 4 pi times 10 to the minus 7 times 5 divided by 2 pi. I guess I didn't need to write all that twice. Times 0.08. 1, 2, 3, 4, 5. Tesla, right? B fields are Teslas. 1.3 times 10 to the minus 5 Tesla. And then that's the magnitude. We're going to add a negative sign to it when we're adding the two together. But for now, we'll leave it as positive. So B2, same idea. The distance is now different, right? The current, they had the same current value, but the distances were different. Wire 2 is 0.16 meters away, right? It's 0.08 plus 0.08 meters away. So not so bad, right? It's kind of fun. Not too bad. Not too bad. So basically, it's going to be 1.3 divided by 2, right? 1.3 times 10 to the minus 5 divided by 2. But we'll go ahead and calculate that. All right, so now we know how to add them together. So add. Step 4, add. B total is going to be negative 1.3 plus 0.63, which gives you negative 0.63, because it's half. Okay, so we're doing vector addition. Just have to use the right-hand rule to find the direction of the vector now. Okay. I always put one of these on the exam. I always put one like this on the exam. could have different current values, you know what I mean? Same direction, different direction, right? There's many ways I can mess around with this. But it should be a pretty straightforward computational problem, calculation problem. Okay. Any questions at all about this? Right-hand rule is going to be your best friend. Okay, let me go back. So I drew it, a different way. So if you look the way that they draw it, they turn this picture like by 90 degrees so that the wires are coming straight out at you and the B fields are left and right. Okay, this is just a different perspective from what I drew, but it's the same picture. However you visualize it, the best works, either way works. So, there's another example. I'll let you guys do it, but you can see the setup is very similar. So this one will be like a do at home. So then we started talking about current loops. So the magnitude of the magnetic field in the current loop looks very similar, right? Except there's no pi in the denominator. The pi is gone, okay? The pi is gone. The other distinction between this equation and the other one is that this B field is only accurate and true for the center of the loop. At center of loop. Okay? Whereas the previous equation, right, you could calculate P over here, you could calculate P over here, you could calculate P over here, right? Here, this equation is only valid for the very center of the loop, okay? And then when you have multiple current loops, like a solenoid, all you're going to do is multiply by n the number of loops or turns. We call them turns in the solenoid, okay? So, I said I was going to come back to this, but because we still have some more to finish up, I want to have this one as a do at home, okay? So do this one at home. All the steps are kind of there, but try to do it on your own. Oh, this thing is blinking at me. Am I running out of battery? Okay, less than 1 hour. Well, we'll see what happens. The other battery's okay, same with this, do at home. It's going to be very similar to the previous. Okay, so we're talking about solenoids now. And so solenoids are the multiple loops of current carrying wire. And solenoids are important because that's how we create magnetic fields, medically, for medical applications, for scientific applications. We create magnetic fields by wrapping multiple loops of wire around a tube and then turning up the current, okay? And the reason why we do that is because inside of the tube, we are creating a very uniform magnetic field, okay? It's very well, well understood in there, nice and straight. So, the magnetic field at the center, anywhere in the, in the center of the solenoid, doesn't depend on the radius, is going to be mu naught and I over L. So this is anywhere inside of the solenoid. Anywhere in that tube. Okay, here, 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 here. All those magnetic fields are the exact same value anywhere in the tube of the solenoid. So we did this right-hand rule. Okay, this one's a little tricky for a lot of people because you have to visualize, what is behind the loop and in front of the loop, right? This current carrying wire here is behind the loop. So when you're doing your thumb in the direction of the current on the right-hand side of that solenoid, right, you're going to stick your thumb in the direction of the current and you're going to curl them around until your fingers are in front of it. And then you can see that the magnetic field direction points in the direction of my 4 fingers, right? Because I'm sticking it up, but since I'm behind, I'm at the back end of the loop, I'm gonna rotate my hand until my fingers are in front of my thumb, which is the current. And you're gonna see the blue vector arrows are gonna be in the same direction as my hand, my fingers. Okay. So when you're dealing with solenoids and perspective, you know, definitely keep that in mind. So we did this, we did this. This one I think is like a do at home. This is a very easy, this one's easy. We're gonna skip that one. Okay, so what we're gonna get to, okay, so this is kind of like a summary, right? So what we have been talking about so far is magnetic field lines coming out of magnets and magnetic field lines coming out of current carrying wires, okay? So this is gonna give you a nice summary of all the different geometries that we looked at, okay, and all the formulae. And this is kind of this is a good example that kind of like wraps everything up. Let's do it. I think this is a good one. And then we'll start with something kind of a new right-hand rule. So we want to know what is the magnitude of the magnetic field right here at the center of this circle, okay? And the idea here is that there's 2 contributions to the magnetic field. We have a magnetic field created by the straight current here, but then we also have the magnetic field created by the loop of current. So we're going to have 2 B fields. So B straight, which is equal to mu naught I over 2 pi r, little r, and then B loop, which is equal to mu naught I over 2r. And I'm going to put this as capital R because this is like a fixed value, where little r can be any value. Okay, capital R means constant value. So we know that here's how we calculate the magnitudes of those, okay? Let's find the directions first. I like to find the directions first. So let's find the directions first. So let's find the direction of the magnetic field due to the straight wire. So my thumb is going to go in the direction of the straight wire's I, which goes like this. And then I'm going to curl my fingers, but I'm going to stop them when they're below the wire, right? Because point P is below the straight wire. So my fingers are pointing into the page. So my B field due to the straight wire is going to be into the page. And then what about my loop? So my fingers, you might be tempted to curl them like this, but your fingers are the current direction, so my fingers need to follow those curved arrows, okay, like this. And then I'm going to spin them around that current. So what I'll do is I'll park my thumb right here. Okay, that's my thumb. And the point P is to the right, so I'm going to stick my fingers and I'm going to stop them when they're to the right of my thumb. And they're going to be pointing into the page as well. See that? So B loop also points into the page. See if I can draw that. There's my weird fingers. They're like witches' talons. So also into the page. So I'm going to add these 2 up together. They're not going to be subtracted, right? They're just going to be added together, and I know that my total magnetic field is going to be some total value pointing into the page. So now I can figure out what those magnitudes are. I'll write it over here. So the magnitude is mu naught I, so 4 pi times 10 to the minus 7. And then the current is 3. And then 2 pi, and then how far away am I from the straight wire? I'm a distance r away, which is 4 centimeters. So that becomes a 2 times 10 to the minus 7 in the numerator. Okay, so 15 times 10 to the minus 6, or 1.5 times 10 to the minus 5. And then B loop will be the current is still 3 amps. And then now I'm simply doing 2 times R. So in the numerator I have 2 pi. Okay, so 15 plus 47. So my total is going to be 62 into the page. Okay, so vector addition. Yeah. No, they'll all be coaxial. Maybe not pointing in the same direction, but yes. Yeah, you won't have like an X and a Y to add together. Yeah. So we're good now. I think, yeah. So I'll keep it all along the same axis for sure, the B fields. So we're going to kind of switch gears a little bit. Okay, we're going to talk about another right-hand rule, and the fingers are going to have different roles now. Okay, so we are going to look at the forces that are exerted on charged particles when they're floating around in an electric field. Okay, so kind of to kind of like link it to what we just looked at. Currents create magnetic fields, right? Currents are moving charges. Well, they create magnetic fields and they also feel magnetic fields, right? They feel forces due to them. So not only do moving charges create magnetic fields, they can feel a force due to a magnetic field. That's what we're going to look at. So magnetic fields also exert forces on moving charged particles, like a current, right? A current is a bunch of moving charged particles, positive ones, right? Currents are always positive charges. But we're going to be looking at positive or negative charges. But this is just kind of a reminder, right? Currents are always positive charges. So we're going to look at some experiments, okay? We're going to qualitatively look at some stuff, right? So the experiment goes as this. If I fire a positively charged particle, okay, and I get it to move with speed v, or with no speed, okay? Never mind. I'm starting with no speed. So charged particle sitting in a magnetic field, he's not going to feel a force, okay? So if the particle is not moving, he won't feel a force, okay? Second experiment. I'm going to fire the particle along the magnetic field direction. He still won't feel a force. There's only a certain configuration where that charged particle feels a force through the field. And that configuration is when there is some angle between V and B. Okay? So when the velocity vector of the charged particle and the magnetic field have some angle in between them, then you're going to get a force. Okay? But that force is not going to be along B, okay? It's going to be perpendicular to B. It's going to be actually perpendicular to the plane created by V and B. Oh, sorry. Because you can create a plane with 2 vectors, right? Just like an X and a Y, right? An X and a Y together, do this, right? An X and a Y vector together create an XY plane. A V and a B are going to create a VB plane, and the force will always be, the force created by that magnetic field will always be perpendicular to the plane created by the two vectors V and B, okay? So the force is the greatest when those 2 vectors are 90 degrees from each other. That's when we get the greatest force. So this is us in the lab, like figuring all this out, okay? And so what all these culminate together, the experiments, you know, this is just kind of like a reiteration of the experiments. I don't need to read that to you. And so what they all culminate together to do is to tell us that the force is always perpendicular to the plane created by V and B. And so there's two ways that that force could point. It could point perpendicular up or it could point perpendicular down, okay? So that's where the right hand comes in. The right hand tells you if it's going to be an upward or a downward force. So the right hand comes in, you put your fingers in, or, okay, well there's a couple ways to perform this right hand rule. Let's do the one in the picture. Thumb is in the direction of the velocity vector. Pointer is in the direction of V, and then your middle finger is the F vector. Okay, so it's helpful to remember that. Middle finger is the F vector. So what you're creating with your fingers is you're creating like X, Y, Z, right? Your thumb and your pointer are flat, right? They're creating a plane, and then your pointer sticks straight up. I love this. Just kidding, I don't. I feel bad. Put it away. This is why I like the other right hand rule. So there's another way to perform this right hand rule. What you could do is you could put your four fingers in the direction of V. Okay? And then you're going to curl them into B. And then your thumb would be the perpendicular vector F. So if you start Googling right hand rules, you're going to see a bunch, right? So your fingers are going to curl. Imagine this is like my knuckle. These are knuckles, and then this is like my pointer finger with my, witch's claws on them. Let me see if I can draw it nicer. Right, oh my gosh, I don't know. I need to work on my hand drawings. This looks terrible, that looks worse. Okay, like here's my knuckles, okay? And then F is my thumb, and then I'm starting my fingers, okay, let's do this. I'm starting my fingers in V, and then curling them into B. Right, with your right hand, there's only one way to sweep your fingers, right? Your fingers only curl one way. Your fingers don't curl like backward, right, of your right hand. You only curl one way. So you put your fingers in V, curl them into B, and you can see like what the sweeping motion, the curling motion is creating that plane, right? And your thumb is perpendicular to the plane. So up to you what you prefer. I like to keep, because this is kind of the same hand motion as the other one. You know what I mean? So F is your thumb. This is a thumb. Whichever, works for you. Whichever works for you. So we use the right hand rule to determine the force direction. So take a look, this picture, the right hand rule is for positive charges. Okay, right hand rule, RHR, works for positive charges. So that's going to tell you the force direction of a positive charge. But as you know, some charges can be negative, right? So for negative charges, you use the left hand rule. Use the left hand rule. So for negative charges, okay, so we have a negative charge. Our B field, our velocity is still to the right. I'm going to draw it just like this picture. I should have used a different color. Our B field is going like this into the page. Our F vector for a negative charge is going to be pointing down. It's going to be opposite to the force vector that a positive charge would experience. And you can use your left hand to figure out the force direction of an electron, okay? So if you see that your charge is an electron, use your left hand. If you see the charge is a proton, use your right hand. So we're going to use the left hand rule for this guy, for negative charges. Or you can use your right hand rule and then just flip your answer. But sometimes we forget to flip it, so that's why, I don't know, it's a good idea to just think left hand. Okay? We'll do lots of examples. So what is that? So what is this formula? What does it spell out? Right, so we use our right hand rule or our left hand rule to determine the direction of the force. Well, what's the magnitude of the force? The magnitude of the force is QVB, Q being the charge, V being the velocity or the speed, B being the magnetic field, and then sine of the angle in between V and B. Okay, so the angle between V and B, just as a reminder, the way that you determine an angle between two vectors is you put them tail to tail. So V and B need to be sitting tail to tail. I think most of the pictures will be like that. Like these are technically sitting tail to tail, right? Because like you draw them back, right? So then this angle right here would be alpha, but you know, they might try to mess around with you, okay? And you just need to make sure that if you're calculating angle alpha, that you're putting those two vectors tail to do it. That's the only way you can calculate the angle between two vectors. All right, so let's do this. So we're gonna combine two concepts. Concept one, the magnetic field direction due to a bar magnet. Concept two, what is the force acting on that positively charged particle? So we're gonna use our right hand. So the V vector is clearly demonstrated what direction the V vector is. The B vector is going to be going this way, right? Because we're going to follow those magnetic field lines and take the tangent. So B is going to be going that way. So we use our right hand. We'll do my version. So fingers in the direction of the velocity. So they're going up somehow, okay? And I don't know how to rotate my hand yet, but their fingers are going straight up. I need to curl them into B, so I'm going to need them to face this way and curl into B, right? Because B is pointing to the left. And then the thumb direction is out of the page, right? Fingers in the direction of B. I'm going to spin my hand so that I can flop it into B. B is a boy. And then my thumb is going to be out of the page as a result. Out of the screen. Okay, so we should get out of the screen. Let's do the other right hand roll if you want. Okay, so F is your middle finger. V is your thumb. B is pointing to the left, and you can see that my middle finger is also pointing out of the page. So they both work. It's whichever you're most comfortable with. Let me draw the F vector here. So F would be the dot, right? Because it's out of the screen, is a dot. So right hand rule, okay. The tactics box is kind of giving you a little summary, giving you kind of like a step-by-step how to complete these problems. Here is where you can see that the right hand rule switches to the left hand rule when you have a negative charge. Okay, here they kept the right hand, and then you can see that your force vector is going to be opposite to your middle finger. But if you use your left hand, okay, thumb in the direction of B, B pointing that way, you can see that you get the upward vector if you use your left hand. So it's up to you. Choose your own adventure. Okay, so let's do this. So we're going to have to first figure out what the magnetic field direction is and then the force. And we have a negative charge here. So magnetic fields, we're outside of a magnet, okay? We're pointing from north to south. So our B field goes like this. Okay, our V is down. Make it green like the other one was. So, and it's electrons, so these are left hand. So I'll do the 3-finger one. So thumb is velocity, so I'll turn that upside down. My pointer is B, so I'll rotate my hand. And then you can see my middle finger is pointing into the screen. Okay, and that's my left hand. Let's confirm. So F is pointing into the screen. That's an X. We can confirm with our right hand and just flip the answer, right? Thumb in V, pointer in B, fingers pointing out, middle fingers pointing out, but it's my right hand and it's an electron, so I need to flip my answer, so it should also be pointing into the screen. So it's into the screen. And so which way is the electron going to be deflected? It's going to be deflected into the figure, right? Into the plane of the figure, into the screen, into the paper. Okay, into is our X. Okay? So, you know, we have a compass built into our phones. There isn't a needle in there, okay? It's a digital compass. And so it detects Earth's magnetic field by calculating the force that is exerted on the moving charges in the phone. So if we have a magnetic field pointing up and the moving charges are electrons pointing to the right, what is the direction of the force? Okay, so let's use our left hand. V is our thumb, B is our pointer, and then my middle finger is pointing into the page. Right, into the page, into the page. Okay. Here they're using the right hand and they're flipping the force vector, but I use my left. Okay, so nothing too crazy. So what happens if a charge is traveling in a magnetic field? Okay, it does something funny. It starts moving in a circle. And I think that'll make perfect sense once we sketch the forces on it. Okay, so when a charged particle is flying around in a magnetic field, it's going to constantly feel a force turning it in a certain direction, right? Just like this guy up here. This charge is going to constantly be turning into the page, and then kind of like in that same direction, it's like it's going to be moving in a circle because there's constantly a force acting on it to turn it, right? So it's going to start moving in a circle. This circle is like into the page, out of the page. Circle. Okay? So that's the general idea. So it's going to be moving in circular motion, and the speed on it is going to be constant. So why is it going to be constant speed? Because the force acting on it is constant, right? Sum of all forces acting on the particle, there's only going to be the magnetic force, which is QVB, right? Sine angle between. So the force is constant, which means the acceleration is constant, right? Because we know that the sum of all the forces is going to equal ma, where the sum of all the forces is just the one magnetic force, right? So if F is constant, A is constant. If A is constant, then, oh wait, hold on. No, then the velocity is not constant. If A is constant, the velocity is changing, right? Let me think. Moving perpendicular to, there's an additional force that is keeping it zero. And that is, for example, well, we're going to get to it. I don't think it's been introduced yet. But this is the idea, right? The sum of all forces is going to equal ma, where the force is QVB. Let's stick with that, and let's open it up a little bit more. So a particle moving in a magnetic field is going to constantly feel a right turning or a left turning force, right? It's going to constantly be turning. And therefore, it's going to be moving in a circle, right? Because the way you travel in a circle is you constantly make a left or a right turn, okay? That's how you move in a circle. So the magnetic field is constant, and so the force will be equal to QVB. The sine is going to be sine of 90, which is 1, right? Because everything is perpendicular to each other. The B field is pointing into the page. The velocity is perpendicular to that. And so the force will be perpendicular to those two vectors. So how does it move in constant speed? Well, here's where it comes in, right? For an object moving in constant speed in a circle, this is called uniform circular motion, and if we're going to pull back something from physics 1, okay? And I'm going to explain it to you now, so it's not like, oh, was I supposed to remember that? We're going to recall it together, okay? You might recall that you have an acceleration called a centripetal acceleration, and that centripetal acceleration is equal to v squared over r, okay? So that centripetal acceleration, v squared over r, even though there is an acceleration present, the particle is moving in a circle with constant speed. So that can get a little tricky. And it's because the acceleration vector, because obviously things that accelerate, their speed will be changing, right? But not if the acceleration vector points in a perpendicular direction to the speed, right? V is up here in this picture. The acceleration vector direction is this way, right? Because remember, centripetal acceleration points, or another word for it is radial acceleration. You might have seen it phrased like that. They mean the same thing, okay? It points in the radial direction, which is perpendicular to the velocity. So that acceleration pointing in the radial direction is not going to change the speed of the particle moving in a circle, okay, because it's perpendicular to that velocity. The only time you get a velocity change is if your acceleration is pointing along the velocity direction, right? Then you're speeding up. And if it's pointing opposite to the velocity direction, then you're slowing down. But if it's perpendicular to the velocity, you're not changing the velocity in that direction. So that's why you can have an acceleration, but still have a constant v, okay? So what we're going to do is we're going to add up all the forces on that particle, which is only the magnetic force. And then instead of setting it equal to m, well, we're going to set it equal to ma, but our a is going to be the centripetal acceleration v squared over r, right? This is our acceleration, our radial one, otherwise known as centripetal. And I think there was like even a third word for that, centripetal, radial, I don't remember. I thought there was like a third. Tangent. No, tangent's the V. Anyway, so we're unlocking something. We're unlocking an equation that represents the motion of a charged particle in a magnetic field. We're kind of deriving it, okay? And so this is going to be the fundamental equation. Those two together are going to be the fundamental equation that governs the motion of that charged particle moving in a circle. So we can rewrite it in terms of radius. If we wanted to solve for radius, you could rewrite it to solve for magnetic field, right? Depends on what you're solving for. But this is the core equation right here. So from that, we can solve for r, sure, right? Sure, we can solve for r. And we can see that the radius of the circular orbit is going to be related to the velocity of the particle, the mass of the particle, and then the charge of the particle, and then the magnitude of the magnetic field. Okay? But this magnetic field is only the magnetic field that's perpendicular to the velocity. Okay? It's only the B component. This is B, the B component that is perpendicular to V. Because how did we arrive at that equation? This one is the picture that we set up, remember, is B is pointing into the page, V is going this way, so that B is 90 degrees with respect to V. So if that B had like some other component, so here's where some XY stuff could come in, right? Someone was asking about the XY, right? If B was pointing in some other direction, then we would need to know what is the component of B that's perpendicular to V. That is what goes in this equation, okay? So there's a caveat, right? This B is the B that's perpendicular to V, okay? So, well, what if the velocity is not perfectly perpendicular to the magnetic field? What happens? Okay? If let's say only one component of the velocity is perpendicular to the magnetic field. What does the other one do? Well, the other one makes the particle just continue to go straight, right? So you're gonna have a particle that's moving straight due to this component of the velocity that's parallel to B, but then you're gonna have that perpendicular to component that's gonna cause the particle to move in a circle. So what you're gonna get is a helix, right? A helix is circular motion with like a straight component to it, okay? So if the particle's velocity is not perfectly perpendicular to the B field, then what you'll get is a helical motion instead of just a circle, a flat circle. Right? So if you're looking straight down, you're only gonna see circular motion, but if you tilt this to the side, you're gonna see that it's circular motion with a kind of a parallel component, right? It's stretching out that circle. So you're gonna get helical spirals. So that's for when you have two components of the velocity, one that is parallel to B, creating the height of this helix, right? That's there because you have a V parallel, and then the V that's perpendicular to B is going to be causing the circle motion. So where do we see this? So this effect is why we see the aurora borealis, the northern lights. So when Earth's magnetic field, Earth's magnetic field is, going its directions, right, north to south, okay? And then you're gonna have the sun has these coronal mass ejections. I don't know if you've heard of that. A coronal mass ejection. So basically like some part of the sun blows up and it shoots some crazy charged particles out heading towards Earth. Well, those crazy charged particles are going to get trapped in the magnetic field of Earth, right? That's actually the purpose of Earth's magnetic field. It protects us from these charged particles. So if we were outside, out in outer space and we didn't have our spacesuit, we would get cancer like really fast because of these highly charged particles, hitting us. But the Earth's magnetic field protects us from those. And we can kind of see that protection because when we have a bunch of those particles coming towards Earth, they're going to get stuck in Earth's magnetic field, moving in helical patterns, and they're going to produce these lights, okay? The northern lights, because those particles are going to hit the gas of our atmosphere and ionize them. And so when it hits the nitrogen particles, it's going to cause an emission of a certain type of light. When it hits the oxygen particles, it's going to cause another color. When it hits, hydrogen particles, it's going to cause another color. Okay, so those are the colors that you see is the interaction between the highly charged particles hitting the molecules in our atmosphere and causing them to break apart and release a photon, which we will talk about in a few chapters. Okay? So let's do some more kind of right-hand rule-y stuff. Let me see where we are. We're gonna hurry up. We don't have time to do too many. Okay, let's just do this one. So the question is, we have our charged particle, positive charge. We know the force direction. Okay, the force direction is up. We know that the particle is moving with the velocity into the figure. So the V direction is, into the page. Okay, which is like an X, right? The question is, what's the direction of the magnetic field? So we're gonna have to do a right-hand rule, okay? But we're gonna align velocity with force to find the B field, the pointer's direction. So I'll take my thumb and point it in the velocity direction, which is into the page. And I'm using my right hand because it's a positive charged particle. And then my middle finger needs to be forced. So I need to rotate my hand so that my middle finger is pointing up. And then I'm going to look at the direction of my pointer finger, which is the magnetic field. And you can see that the magnetic field is pointing from right to left, right? It's pointing to the left. So my magnetic field is pointing to the left. And if my magnetic field is pointing to the left, that means I have like a north pole on this side and a south pole on this side. So the magnet's north pole is on the right, and the magnet's south pole is on the left. Okay? So we're doing the right-hand rule, but you're kind of finding an intermediate vector. You're not, you know what I mean? You're not finding the resultant force. You're finding one of the intermediate vectors. So be prepared to do that, because that shows up on the exam a lot too. I'll have you find V or B instead of F. Okay? So do lots of them like this. So basically these quick checks I'll ask you guys to do at home just because of time. And I want to show you these demos. Okay, so do at home. These are all right hand or left hand rules, right? Look at that, left hand rule. Don't forget, it's a negatively charged particle. Okay, let's do this one real quick. Okay, because this one kind of has like a hidden, it has a, you know, you're bringing in a concept from electric fields. So let's look at this. Which would be the correct magnetic field direction that would allow the electron to pass through without being deflected? Okay, so what? So the idea here is that, look at these plates. These are not magnetic plates, okay? This is this is like a parallel plate capacitor. So this is creating an electric field pointing down, okay? All right, this is all a bunch of electric field lines pointing down, right? And we know that when a particle enters an electric field, it's going to either move with the field or against the field, right? Depending if it's a positive or negative charge. So what do we have here? We have an electron. So the force direction due to the electric field is going to point up, right? Because it's negative E times the electric field, right? And that negative sign is going to flip your direction. So our force is going to point up due to the electric field. But if there's a magnetic field as well, okay, then there's going to be an additional force vector. And so let's read the problem. We want that charge to pass through without being turned by the magnetic field, right? So in order to counteract the turn of the magnetic field, that's what the electric field is going to do. So essentially, what the question is asking you is, well, FB would need to point down, right? So that the sum of all the forces in the Y add to 0, and you don't have any bending. So what the question is ultimately asking is, if the force FB is pointing down, and the velocity is pointing to the right, what direction would the magnetic field need to be to create that downward force on the electron? So I'm going to use my left hand, because it's an electron, and I'm going to put my fingers, let's do this one. I'm going to put my thumb in the velocity direction, which is this way. And then my middle finger, which is the force due to the magnetic field, is going to point down. So I'm going to rotate my hand. And you can see that my pointer, which is the magnetic field, is pointing into the page. I'm using my left hand because it's an electron. Okay, so FB is down, that's my middle finger pointing down. Thumb is to the right for velocity. Pointer finger of my left hand is pointing into the page. So I'm going to need an end of the page magnetic field to give me that downward force of the magnetic field to counteract the upward of the force due to the electric field. So we're kind of taking two concepts, putting them together, right? So that's how we get a particle to move straight when it's in a magnetic field, because we don't always want the particles to turn, right? So if we want to counteract the turn due to a magnetic field, we're going to apply an electric field to oppose that magnetic field. So what I want to jump to is this. So obviously, if single particles feel forces due to due to magnetic fields, then currents are going to feel forces due to magnetic fields, right? Because a current is simply a collection of charged particles. So we're gonna use essentially the same right-hand rule, except instead of our velocity being of one charge, our velocity is going to be the current direction, right? Because the current direction is the flow of positive charges. So we'll use our right hand. So whenever we're finding the magnetic force due to a current, you're always going to use your right hand because your current is always the flow of positive charges. So let's do the right hand rule on here. So we have our current going up in the wire. So our thumb is our velocity direction. Our B field is our pointer, which is pointing into the page. So I'm going to rotate my hand. And you can see my middle finger, the force, is pointing to the left. Okay? Same idea as single charges, because a current is just a collection of single positive charges. Okay? Same exact right-hand rule. Let me show you the equation. Very similar structure. Instead of QVB, it's ILB. Okay? Where I is the current, L is the length of the wire. Okay, and then alpha again is the angle between the two vectors. The IL vector, right? The IL is simply this vector right here created by the current and the length, and then the B field. So we'll, maybe we can do a couple of these next class. I want to get to these demos here real quick. Let me show you this. We can do maybe do a couple more. So here I have a magnet, okay? The north pole is up here, the south pole is down here. So the magnetic field direction is pointing from north to south. So the magnetic field here is pointing down. I'm going to hook up and get some current flowing in the yellow guy, okay? And so the current direction, we're curious about the current direction in the field, right? We don't care about these because they're not in the magnetic field. So the current direction here could either point to the right or to the left, depending on like the polarity, right? I'm gonna do both. And so then there's gonna be a force acting on that wire due to its existence in the magnetic field, and let's see an evidence of that force. So I think I need to do this way first, and then turn it on. Whoop, right? The sound pop out. Popped out. Force is pointing outward. So let's do the right hand rule to confirm that, to see what direction the current is flowing. So my B field is pointing down, B is the pointer. My force, my middle finger, was pointing outward, it's being pushed out, so I'm going to rotate my hand. And so my thumb is pointing to the right. That must mean that the current flow is from left to the right. And so what I can do is I can take this switch in the back, and I'm going to reverse the polarity. And you can see that the wire gets sucked in this time, right? I switch to the current direction, and I got the force to go in the opposite direction. So what we're going to look at here, right, is two parallel wires. So let me skip to the two parallel wire section, right? Because here we're still in the one wire in a B field. So I'm going to skip down to the last section, which will be the last thing we're going to talk about. Oh, here, I guess it's technically in this section here. Okay, it's technically combined in this section. What about two currents? Okay, so how does two currents work? Technically the class is over, but I'm going to go a little bit over. And so if you have to go, you can leave, of course, but I'll just go a little bit over just to illustrate this. So what happens when you have two currents? Well, one is a current creating a magnetic field, right? And the other one is a current that's going to feel it. And then their roles are interchangeable, of course, right? Because both can feel a magnetic field, and both can create a magnetic field. So wire 1 is going to create a B field, and wire 2 is going to feel it, right? So in this picture, wire 1 is here on the left, and you can clearly see it. And wire 1 is going to create a B field. And you can do the right-hand rule to verify that, right? It's going to come out on the left and go in on the right. Well, if I stick a wire right here, okay, he's going to be exposed to a magnetic field pointing into the page. And he's going to feel a force as a result. And the force that he feels is going to depend on if the current is going up in the same direction as I or down anti-parallel to I. So we can kind of look at both cases. So let me show you. I'll show you both cases in real time. Let's see if I can line this up. Okay. All right. So what we're looking at. I wonder if I could put a piece of paper or something there. Okay, so we're looking at the 2 yellow wires. All right, so let me see that a little bit. Okay, I want you to look at the 2. Let me focus. Okay, we're looking at the 2 yellow wires, and one of the black ones in the back. Okay, and so what I'm going to do is I'm going to send in a current. Parallel and anti-parallel. So right now I'm in the anti-parallel direction, and let's see what happens when I follow the current pass. Ooh, they got popped out, right? So they felt a repulsive force. So anti-parallel currents give you a repulsive force, and we said that I need to squish it while it's closed. Surround. Okay. Oops. It's got caught. There we go. Right? Now we're going to switch to parallel. You saw them get stuck together, right? So anti-parallel, I'm going to turn this off because it's like smelling bad. It's very high current. So what you're going to see is that to get a strong force enough to see it, you have to pump like a ridiculous amount of current in there. You can't leave it connected for too long or else it gets really hot and start burning plastic things. Okay, so anti-parallel is repulsive force, parallel is attractive. And the way you can remember that is it's the opposite of like everything else, right? For north and south pole, right, opposite poles attract, opposite charges attract. Well, guess what? Not here in force between wires, okay? So that's kind of the way you can remember it. So you get an attractive force when the currents are parallel, and you get a repulsive force when the currents are anti-parallel. So here's kind of that summary right here, okay? And the magnitude of that force is given up higher, where we kind of skipped it a little bit, okay? The magnitude of that force, well, maybe they didn't give it. Well, there's an equation for the magnitude of the force, okay, the force per unit length. And so that's essentially, the end of magnetism, right? We looked at the magnetic field. Oh, sorry, you can't see what I'm looking at. We looked at the magnetic fields created by current carrying wires, and then we looked at the forces that charges and currents feel when they're in a magnetic field. Okay, and then we looked at them both combined, right? Both concepts are combined in the parallel wires topic because each wire is both producing a magnetic field and feeling a force due to that magnetic field. So I'll talk, we'll wrap up just a couple more, maybe we'll do one more example next class, but we'll basically start a new topic next class. We're going to talk about changing magnetic field and what happens. Okay, let me know any questions.